Hello, it's Ryan. This is our first example of projectile motion. I've written it out to save us a little bit of time, and I started the picture, but we'll kind of continue the picture together. So this reads, we launch a crate full of fruit off the Burj Khalifa in Dubai. The Burj Khalifa is the tallest skyscraper in the world, so we are launching our crate 829 meters above level ground. If we launch the crate with a horizontal velocity of 41 meters per second, determine the time the crate is airborne, and B, the impact velocity of the crate. So that's what we're looking for, two values in the end. And believe it or not, this is written well, and it gives just enough information to solve the problem. So first step of any problem solving for us should begin with draw a picture. So, we should draw a picture, and like I said, I began doing that. So this is our draw a picture. And I put the Burj Khalifa, which that drawing isn't great, but it actually does kind of look like a side profile of the building. And then I put our crate full of fruit, and I put a couple pieces of fruit in there. So there you go. So now what we want to do is we want to add anything that we know about this picture into our drawing. So let's go ahead and label the initial velocity of the crate, V sub O. And how did I know the direction of V sub O? How did I know how to draw that vector? Well, it's given in the problem, of course. We're told that the crate is launched with a horizontal velocity. So our launch, or our initial velocity, should be only in the horizontal direction. So that's why I drew it that way. We can also show the path that the crate will take through the air. Being launched horizontally means we'll get this kind of half parabola. And we could show then, of course, that the acceleration due to gravity is the only thing acting on the crate. So we should show the acceleration due to gravity's vector. We could also show that the crate's going to impact the ground down here. And I'm going to actually draw our crate just before it hits the ground. And then we can show that that's going to have some impact velocity. Like so. Okay, so is there anything else we should label? Well, I think so. I think we should show that this thing, of course, is launched from some initial height. We can call that h. It's launched from some height h. We could also kind of show that we're going to begin our xy coordinate plane down here. So we're showing that this point that we're launched from, this launch point here, is going to label our 0, 0 point on our axes. And so we could also show that really then we have some initial y position up here. So this is our initial position. So S sub O. In the x direction, it will be 0, and in the y direction, it will be h. And our final position, S final, will be something maybe we could call x and 0. And so we could show that this is x, our horizontal displacement. And h is, of course, our vertical displacement. And we could also show then maybe that this velocity here has a horizontal v impact in the x direction and v impact in the y direction. And maybe we could show that there's some angle here, phi. So there we have it. Now what I think we should do is give our knowns and unknowns. But this time, when we do our knowns and unknowns, I think it might be helpful to give the x and y directions kind of separate from each other. So we could have x direction and y direction knowns and unknowns. You don't have to do this, but I don't think it would hurt. And something else to keep in mind when you're looking through knowns and unknowns, we really only have 3 measures of motion that we want to kind of keep track of. So you might, since this is our first time, you might note our measures of motion that we want to keep track of are, of course, displacement, velocity, and acceleration. And so for all of these x and y directions, we could have a x sub o, a y sub o. We could have our x final position and our y final position. That takes care of our displacements. Now our velocities, we could have a v sub o x and a v impact x. So that means we could have v sub o y and a v impact y. And then we could always have an acceleration, a in the x direction and a in the y direction. And so that really keeps track of any measure of motion that we may need. So again, this may be a little excessive, but it can't hurt. It will help us to not have to reread so often. So let's go ahead and put out these numbers in. So we know our x sub o, our initial position in the x, is 0, and our initial position in the y is h. We could have made our initial position in the y 0 and our final position in the y h, but this seems like it makes more sense logically. So down here, we're saying is y equals 0, the final position in the y. And our final x position, well, we don't actually know that, do we? We just called it x in our picture, so I'm just going to label it x. That's one of our unknowns. Okay, we know v sub o in the x direction is just v sub o, which is the 41 meters per second. That means v sub oy is 0 because it's only being launched horizontally, which we discussed in the beginning, but we also showed in our picture there's no vertical component to our initial velocity. V impact in the x direction, well, we kind of do know that, but I'm just going to note that we might not know it yet, just in case. ax, well, acceleration, what is it? It's, of course, the acceleration due to gravity, and that's it, which is in the vertical direction. So when we say ax, we know that must be 0 for any projectile motion problem in particular, but we also showed that in our picture by drawing the vertical acceleration vector. And that means that AY will be 9.81 meters per second squared, the acceleration due to gravity at the surface of the Earth. But we have to be careful. In our knowns, we've decided that up here is some positive value for height, and down here is some 0 value for height. And so that means that our crate in the vertical direction is going from 829 meters to 0. And so that indicates that this downward direction must be negative. And so we need to put in our knowns a negative 9.81 meters per second squared. And now we have everything we need to start to try to solve the problem. But we're not going to sit and think about answers yet. This was our setup, but we're not quite done with the setup. If you ever had to do any carpentry or any hard labor, if you've ever had to do any hard labor, you know that if you're going to a job site, you want to bring all the necessary tools with you, but you probably don't want to overpack. For example, if you were going to replace the carpet in someone's home, you might want to bring a hammer. You might want to bring a box knife so you can cut the old carpet. But you definitely probably don't need to bring a sledgehammer. Can't imagine needing a sledgehammer while you're putting carpet in. And so you wouldn't bring it. So the whole point of this silly talk is that we need to set up a toolbox for this particular job, for this particular problem. But the way that we'll set up a toolbox in our class is always the same. So this is really how, when we begin solving the problem for any projectile motion. So I'm going to note that for projectile motion problems, we build a toolbox. To build a toolbox, we need only the displacement equation and the velocity equation from the big three. More specifically, what I'm really saying is we won't use the time-independent equation. The other fundamental point that I need to make here is that we will write each equation for each direction separately. Direction independently, so it matches our original language. So this, again, might sound a little strange, but I'm going to show you right now. So we're going to build a toolbox for the problem above, and all we need to do this is our knowns and unknowns. And, of course, the big three. We're going to do this for the x direction and the y direction, independent or separately from each other. And so now would be the time to look back in your notes if you forgot, but we will write the displacement equation and the velocity equation for each of these directions. So instead of writing s for the displacement equation, I'm going to write x. It was 1/2 axt squared plus v sub o xt plus x sub o. And we'll write the exact same thing for the y direction. So it may seem like a very long process right now, but really we're just copying right out of the notes the first two of the big three. So there they are. So step one is, I guess, to write the four equations we need. Next, we want to input any zeros that we have. So looking at our knowns and unknowns, we can see that x sub o is 0, and v sub o in the y direction is 0, and ax is 0. I'm going to ignore the y final right now. So I want to go ahead and use x sub o equals 0 and input that. So we'll use red for our zeros. So x sub o is 0. That's the only place where there's an x sub o. In our list, we also said that v sub o y, the initial velocity in the y direction, is 0. This is 0. But 0 times t is still 0, so this whole term will turn to 0. We noted that ax was 0. The last of our zeros was ax. Well, 1/2 times 0 is still 0, and then 0 times t squared is still 0, so it gets rid of that whole term. And that means this term goes away as well. and we forgot to get rid of v sub o y there. So now we've input all of the zeros. I'm just going to go ahead and also put any constants we know. We know that y sub o is h, and we know that ay is g. So we know ay is g. So I'm going to go ahead and put g for ay and h for y. So all I'm doing is substituting zeros and known values. And now I'm going to rewrite these equations. So we're going to rewrite these equations. I'm going to write x equals, and our 0 goes away. So we're left with v sub o x times time. And this is 0, so we don't have to write that. Then I'm going to write my y equation. Y equals 1/2 gt squared plus, and now this is 0, so we just have the h. We also have vy equals gt, and v sub oy is 0, so we won't write it. And finally, we have vx equals v sub ox. And this is our toolbox for the problem above. So you might note that this gives the position, those two together give the position of the crate at time t, and these give the velocity of the crate at time t. So in other words, our y velocity is changing every second, but what's happening with our x velocity? Look, it doesn't change. There's no factor of t in there. So what this equation says, even though it seems like it's useless, this really does tell us exactly what we knew going into it, and that's that v sub ox is always or constantly equal to the initial velocity in the x direction. So no matter where we are on our path, we could be here, we could be here, we could be all the way down here, but we always know the x velocity of the crate. So this equation seems a little silly, but it really does prove something that we knew going into this if it was a projectile motion problem. Or I guess I should say support. I don't like the word prove, but either way, now we have everything we would need to solve any aspect of this problem. Well, part A is asking to determine the time the crate is airborne. So looking at our equations, we know that the time is here, here, here. But we also know we have a few unknowns. We don't really know the horizontal displacement. We don't know that. We don't know the time. And we don't know the y direction velocity pretty much anywhere, except initially. And we don't know the time. So what I'm doing may seem silly. It may seem like it doesn't make sense, but all I'm doing is showing the unknown values, because when I look at the unknown values, I should be able to see which equation has the fewest unknowns. And it looks like this second equation only has one unknown in it. So we could say we need t. We could say t total maybe, just to, or what we called that in the problem was the airborne time, the time that it's in the air. Another way we could write that is t impact, the time it took to impact the ground. But that's what we need. So let's use, or we'll say using, y equals 1/2 g t squared plus h. So we know that y final equals 1/2 gt impact squared plus h. But we know at t impact, the time it takes to get to the ground, the final height is 0, isn't it? So this would tell us that 0 equals 1/2 gt impact squared plus h. And now we can algebraically manipulate this to solve for t impact. So I'm going to subtract by h, multiply by 2, divide by g. So we have negative 2h over g equals t impact squared. But now I'm going to square root both sides. And so we'll have the algebraic solution for what we're looking for in part A. So what I want you to notice is that drawing the picture and setting up this toolbox is where we spent most of our time. Once we had the toolbox, we did a couple steps of algebra and we got to where the answer can be solved for. So it's very important while you're solving your problems to try to stick to this method. Draw a picture and try to set up a toolbox for any projectile motion problem. Now we're going to go ahead and substitute the values and solve the problem. So we have the square root of negative 2, h was 829 meters, divided by g was negative 9.81 meters per second squared. And this tells us then, if we were to punch it into the calculator, that we would be airborne. It would take 169 seconds for that crate to hit the ground. That's a long time. That's approximately 2 minutes, 49 and a fifth, or 49.2 seconds. So that's a long time to be airborne. But that's the answer for part A. And time is a scalar, so we don't have to worry about direction, right? Part B wants to know the impact velocity. Well, we can write this several ways, but I truly think the easiest way, anytime you're asked for a velocity, is to write it in the vector notation. So v impact is equal to vx in the x direction, and really, let's be more specific. This would be the impact velocity in the x direction, and we indicate that that's in the x direction with our cute little I hat, plus whatever the impact velocity in the y direction is with a cute little j hat. So this is the easiest way to get our answer, because looking at our toolbox, we could solve for v impact using our velocity equations. So we could say that from the toolbox, we know Vx is always equal to V sub O x, which means V impact in the x direction is equal to 41 meters per second. So we know this part, given that it's a projectile motion problem. But we need to figure out what Vy is. Well, Vy from our toolbox is equal to Gt. We want V impact in the y direction, which means we're looking at G times T impact, but we already solved for T impact. So there's a couple ways to go ahead and do this. I personally like to just substitute in the variables. So V impact y is equal to G times the square root of negative 2h over G. And then a little algebra trick. Let's do an algebra check. Can you show that this is equal to root negative 2gh? That'd be worth a try to see how your algebra is doing. Or you could always just go ahead and put in the value we already solved for T impact. So I'm going to just do that because I don't mind if you do that. Most students like to do that. So V impact in the y direction is, of course, negative 9.81 meters per second squared times the 169 seconds that we got for T impact. This is going to be huge. That means our impact velocity in the y direction is about negative 1,658 meters per second. That's ridiculous. This isn't technically realistic because of that pesky little thing called air resistance, because we have that atmosphere we can't really get out of, but we do need the atmosphere to survive. And we'll talk all about that when we get into forces. So right now we're in physics land where there's no air, and this is the speed that the object would be going in the y direction when it hits the ground. So now we can put all this together, of course. V impact is equal to 41 meters per second in the x direction minus 1658 meters per second in the y direction. And this is enough to be a final answer. If you wanted to get the magnitude and the direction of this, what we're looking at is a vector that's really pointed almost vertically downward, because V impact in the x is so much smaller than V impact in the y. This is going to end up approximately being 1 degree. And so you could show that, of course. How would you get this angle? Well, you just do tangent. Tangent of theta is equal to V impact x, the opposite, over V impact y, the adjacent. Then you would do the inverse tangent of both sides to get theta. And we could go ahead and put in the 41 meters per second and the 1658 meters per second. And that's going to give us approximately 1 degree. Very small. But keep in mind, when we measure degrees or angles, this is 0 degrees. And so that is really the angle we're interested in. But isn't it 270 degrees to here, plus 1 for our theta? So we know that the angle phi would be 271 degrees. That would be the impact angle. And then we can get the magnitude of this, the amount, V impact. So V impact, the amount, is always Pythagorean theorem. So it would be the V impact in the x squared plus V impact in the y squared. So the magnitude of V impact would be 41 meters per second all squared plus 1658 meters per second all squared. And this is so small compared to this that we're going to get about 1658.5 meters per second. And so this is one way to write our answer. This is one way to write our answer. The other way you could write it is that V impact is equal to 1658.5 meters per second at 271 degrees. Or you could say 1658.5 meters per second, and you could say at 89 degrees below the horizontal. So there are a lot of ways to say this, but as long as you indicate both magnitude and direction, then that is a final answer. So this is good, or you could have just stopped here. This secretly indicates both magnitude and direction, and this is enough. So I personally like to use the IJ notation. I think it ends up being a little easier, especially with our toolbox. But if you really end up liking magnitude and direction, you can always solve and show this. The important thing is that you always show direction when you talk about a velocity. If I asked you for an impact speed, V speed impact, that would just be the 1658.5 meters per second with no direction, because that's speed. Okay, so that's our first real example of a projectile motion problem. And it seems kind of complicated, but the thing to really take away from this was getting to this point here. This is where the physics is kind of done, and we're now just in a math class. The important part for me, and especially when I'm grading you, is that I'll be looking for a nice picture, your knowns and unknowns, and I'll be looking for a toolbox, and then that you use that toolbox to solve the problem. This is really the best demonstration of our problem-solving methods so far. And so on quizzes or on tests or even on homework assignments, I'm going to be looking for the technique, the problem-solving method that gets you to the answer, and weighing that far more heavily than the actual answers themselves. This may only be worth 5% of the total points, while the other 95% are gathered from developing